Hello everyone. My name is Urvi and I'm a software engineer at Microsoft. And I welcome you to this 5-part series by Scalar where we'll be covering linked list data structure in C++ programming language end to end. Here we'll learn about what is linked list data structure, how it's different from arrays. We'll solve some easy level questions on it, then we'll move on to medium level questions, and we'll also cover some hard level questions on this data structure. Post which we'll cover the variations of linked list, that are doubly linked list and circular linked list. So that after covering this full course, you should be able to solve any coding problem on linked list data structure. So let's get started. So in this first lecture, we'll be starting with what exactly is linked list and why are we studying linked list. What are some challenges that linked list is solving that are faced when we are implementing arrays? And we'll see some basic operations on linked list like insertion, deletion, updation, traversal, and in the end we'll solve some really easy level questions on this topic. So let's get started first of all with what is linked list. In very layman language, I can say linked list is a linear data structure that is used to store a list of items. Okay, it is a linear data structure that is used to store a list of items. Now, I can say the same thing about an array as well. An array is also a linear data structure which stores a list of items. But linked list in some ways I can say is better than arrays. Let's see how. Now there are some challenges that we face when we implement arrays. Okay, what are some challenges? First of all, arrays are of static size. What does this mean? This means that whenever I create an array, I have to specify the size of the array, and then after creating the array in code, I cannot modify its size. So for example, let's take an example. For example, I want to create an array where I want to store the name of the students who enroll in the course. Okay, and for example, I create this array of size 200k, but the number of students who end up enrolling in the course is actually 250k. All right, so now what will happen? The array that I created of size 200k will get wasted. I'll have to create a new array altogether of the 250k size to accommodate all of the students' details. Or another example could be if the number of students who enroll are not more but less. For example, only 180k students enroll in the course. So then 20k of array size would be wasted for me because that would be just lying there idle, and I cannot decrease the size of the array once I've created it. Alright, so that's a challenge that arrays pose, that they have static size. Another challenge in arrays is their memory allocation, which is contiguous memory allocation. Now, what does contiguous memory allocation mean? This means that the memory that is allocated to an array, when I create an array in C++, that has to be present in a contiguous manner in my memory. So how is this a challenge? For example, just imagine that this is my memory, all right, and I need 100 MB of memory, or let's just talk in bits here or bytes here. Okay, for example, I need 100 bytes of memory, and in my memory I have some memory that is free, but one chunk of that memory is 20 bytes and another chunk is 80 bytes. So now you see I do have the amount of memory that I need to create my array, right? I do have 100 bytes of memory that is free. But can I create an array here? No, because the 100 bytes of memory that I need for my array has to be present in a contiguous manner. It has to be present as a block, as a single block of memory. Is that insertion, deletion in arrays is expensive. So once again, imagine we have an array, all right, where we have some numbers 1, 2, 3, 4 and 5, all right, and I want to insert an element 8 here, okay, right here after 2. Right here after 2. Now to insert an element in the middle of the array, what I'll have to do is, first of all, whatever elements will come after it, I'll have to shift those elements. So I'll have to shift 3, 4, 5 first, and then I'll be able to insert 8 here. The same way with deletion, if I want to delete 8, some element from the middle, I can't just delete this one. I'll also have to shift the elements that come after it. I'll have to shift these elements. Alright, and this is given if I have extra space. If I don't have extra space and I want to insert an element in my array, then I have to create a new array altogether. Right, and if I delete elements, then there will be memory wasted. So these are some challenges that are posed by arrays. Now, how is linked list solving this? So I told you that linked list is a linear data structure that is used to store a list of items. Now the difference comes in implementation. How is linked list implemented? Linked list implemented as form of memory blocks that are linked to each other. Memory blocks or blocks in memory that are linked to each other. So for example, I take some block of memory at some random address, okay, and I take some other block of memory at some other random address, and these blocks of memories are linked to each other, and that is why this is known as a linked list. Alright, so just imagine in memory we have random blocks of memory which are linked to each other, okay, and these blocks of memory are storing some values. So this is how linked list is implemented, and how is linked list solving the challenges that are faced in arrays. First of all, it has a dynamic size, meaning that when I create a linked list, I don't have to specify the size of the linked list, okay. I can just keep adding more blocks of memory, more elements to my linked list, or I can keep deleting whenever I don't need. So there will be no memory wasted, and also if I want to insert more elements in my linked list, I don't have to create a new linked list altogether. Alright, so linked list is of dynamic size. I can keep inserting elements, I can keep deleting elements as and when I need. Number 2, non-contiguous memory allocation. So like I said, these are memory blocks that are linked to each other. Now these memory blocks, they don't need to be present all together in a contiguous block of memory. They can be present at different addresses in my memory, and they can be linked to each other. Alright, how they are linked, I'll just tell you, but for now just imagine that these are blocks of memory at different addresses that are linked to each other. So we don't need a non-contiguous memory, so we don't need contiguous memory allocation here. Alright, and the third and last thing, the insertion and deletion here becomes non-expensive. Alright, so here if I want to insert any element in the middle, for example, I want to insert a new element here, after the second element, I just have to change this link. I just have to change this link. I'll remove this link and add new links here. So I'll be able to insert an element, so I don't have to move the other elements anywhere or shift them anywhere. Similarly, if I want to delete this element in the middle, so I can just create this link back and get rid of these two links and the element. So I've deleted now. So here again, none of the other elements have to be shifted, right? So insertion and deletion in a linked list become non-expensive for us. All right, non-expensive in terms of time and space complexity. So these are the three things that make linked list different from arrays and solve some of the challenges that are faced by arrays. All right, now let's discuss what is the building block of a node. So we've been talking about memory blocks, right? I've been talking about memory blocks in linked lists that are linked to each other. So you can imagine, you can call each of this memory block a node. All right, you can call each of this memory block a node. Now a node is made up of two parts. A node is made up of two parts. First is the value, all right, and this is the data that we are storing. This is the data we are storing, that we want to store in our data structure. And the second part is a pointer, okay, or let me call it next. What this is, the second part of my node, this is a pointer to the next node in my linked list. Okay, so this is how these nodes are connected to each other. Each node will have a pointer which will be pointing to the next, just the immediate next node in my linked list. Okay, so for example, I have a node here in which I am storing some value 1, all right, and I am also creating another node. I want to add a node to this linked list in which I have value 2. So for example, if this node is present as address 200, okay, I'm just taking an example here. If this node is present at address 200, so I'll have the address of the next node in the second part of my linked list. All right, so this is how I'll have these two nodes connected. Similarly, I can add another node to my linked list in which I have a value 3, and if this node is present at address 300, so I'll have 300 here, and this is how I'll connect this to this. All right, and this is my linked list. So a linked list is made of nodes. A node is made of two parts. First is the value part, the data that we want to store, and the second part is the next, which is a pointer to the next immediate node in my linked list. Now, how do I know where my linked list is exactly starting? Where is the first node? For that, we take help of another pointer called head pointer. Okay, so the head pointer tells us where my linked list is starting, and if I give you the head pointer of any linked list, so you'll be able to traverse all of the elements in my linked list, right? Because the head pointer will be the first node will be pointing to the second node, so I'll get the second node from there. From the second node will be pointing to the third node, so I'll be able to get to the third node from there, and so on. So if I'm just given the head of a linked list, I can traverse all of the nodes of my linked list. And how do I know where my linked list is ending? That is known because the last node in my linked list, in the last node of my linked list, the next value will be null. It will be a null pointer. Alright. So whenever the next part of any node is null, that means that is my last node in my linked list. Alright, so this is the example of a linked list. Let's try implementing this in code now. So for implementing a node, we'll create a class node. Alright, we'll be taking help of object-oriented programming here. Now I told you that my node will have two parts. Okay, first is the value part. So let's assume that the value we want to store is int, and the second is the next part. Now what will be the data type of next? Next is a pointer to the next node. It's a pointer to the next node. So the type would be node star next. Okay, and let's also create a constructor here. So if I'm passing any value v inside my constructor, so this will just create a new node for me, and it will put v as the value, and it will say next is equal to null. Alright, so this is our implementation of a node, of a single node in our linked list. Okay, how will we create this? For example, if I want to create a new node, I can say node star my name of the node is equal to new node and the value that I want to store in this node. Alright, and for example, I want to add another node in my linked list. So I can say new node 2, and I've stored 2 value in this new node, and I can make node 1 point to node 2. How? I can say node 1 next is equal to node 2. Next of node 1 is equal to node 2. So now these two nodes are connected to each other. So moving forward, let's see how do we traverse. Now I've created a linked list here in code, but how can I traverse my linked list? So I told you all I need to traverse my entire linked list is the head of the linked list, is the starting point of my linked list. So just try to imagine here, this is my linked list and the last node is pointing to null. Okay, and I have the head pointer which points to the first node in my linked list. So to traverse all of the nodes, what I can do is I can take a temp pointer which is at head, and I can keep moving temp by one step. How do I move the temp pointer to the next node? I can say temp is equal to next of temp. So this will move my temp pointer to here because this is the current temp next of temp. And similarly, if I keep repeating this, I will be able to traverse my linked list, right? Now, how will I stop? When will I stop moving my temp pointer one step forward? I stop when my temp is at null. So whenever my temp pointer reaches null, that means my linked list has ended and I can stop traversing it now. Alright, let's see it here. We'll create a function traverse where we'll be passing the head of my linked list. To traverse the linked list, we'll create a temp pointer which will start from head, and while temp pointer is not equal to null, while my temp pointer is not equal to null, I'll keep moving temp is equal to next of temp, and I'll also, before that, I'll also print the current element. Okay, to print the current element, I'll just print temp value. Let me put an arrow here so you'll be able to visualize better. So till the time temp becomes null, we'll keep moving our temp pointer forward and we'll keep printing the values. Alright, so let's create a head pointer here. Okay, we can pass the node 1 also because that's where where our head will be, or I can just create another pointer node star head and make it point to my node 1, which is the first node. Alright, so I'll say here traverse and I'll pass the head of my linked list. So here what I'm getting is a linked list, okay, where the first node has value 1, the second node has value 2, and this pointing to null shows that this is where my linked list is ending. Alright, so this is how I can traverse a linked list. Now let's move forward to seeing how insertion happens in a linked list. And for insertion, we'll be seeing 3 scenarios, okay. First scenario is when we want to add a node at the start of my linked list. So for example, I have a linked list here. I have the head of my linked list and I want to insert a new node. Okay, this is my new node. So step 1 obviously will be to create my new node, and to add it to the linked list, what I'll have to do is the new node should point to the current head. Alright, so I'll say the next of new node should point to my current head, and once I have done that, I'll move my head pointer to my new node, and now I have added an element at the start of my linked list, right? And also, what will be the time complexity of this operation? The time complexity will come out to be O of 1, right? Because we're not traversing the list, we're not moving the elements, we're not doing anything, it's a O of 1 operation, right? We're just changing the links of the node. Alright, so it's an O of 1 operation. Let's see this in code. So void insert at head, and here let's say that we are being given the head and the value that we want to insert, the value of the new node that we want to insert and in our linked list. Now here, when we are passing the head of our linked list, we'll be passing it by reference and by not value. So I hope you understand the concept of pass by value and pass by reference. When we are passing by reference, we are actually sharing the address of our argument here. That means when we make inside this function, when we make changes to our linked list, those will be actually reflected here. If we just pass the head by value, not by reference, then whatever changes we do inside this function will only be seen inside this function. All right, so since we are just returning void here, what we'll do is we'll insert the element in my linked list, and for that operation to show here as well in my main function, I'll pass this by reference. Alright, so I don't have to return anything. Let's do this. First of all, create the new node. Alright, create the new node. So node star, let's call it new node, is equal to new node and the value that I want to insert in my new node. Alright, and now new node next, I'll make it point to my head pointer. Alright, whatever is the current head of my linked list. So I'm adding my new node in the beginning, and then I'll change the head pointer to point it to the new node. So now my linked list is starting from the new node. Alright, let's check this. I'll call this function insert at head, where I'm passing the head of my linked list, and I'll pass the value that I want to insert at the head, which is 3. And we'll call the traverse function again here, so that we'll be able to see the changes made in the linked list. So in the traverse function, why are we not passing by reference? Why are we passing by value? Because we're not making any changes to the linked list, and we're just traversing the linked list in the traverse function, right? So we don't need to pass it by reference there. All right, let's run this. Did we have some syntax error? There's no syntax error, I think just something got selected by mistake. Okay, so we're able to see here this was our linked list before, and I added 3 at the head of my linked list. All right, and even will this function work even if my linked list is empty? So if my linked list is empty, basically the head will be pointing to null. So in that case again, new node next will be null and head will come at new node. So in that case, I'll just be able to add one element, the first element in my linked list. Okay, so when writing these operations, just make sure of the edge cases. What if my linked list is empty? Will I be still able to do this operation or not? Okay. So moving on, we'll be seeing how to insert an element at the end of my linked list. Again, let's try to imagine here we have a linked list with 3 nodes, right? And the last node is pointing to null, and we have the head pointer. So if you want to add a node at the end, all right, that means here, first of all, we'll create this new node. Okay, we created this new node. Now to add this node at the end, we should be able to change this link. We want this last node, the current last node, to point to the new node, and that's how I'll be able to add this at the end. So to do that, first of all, I'll need to get access to this last node. What is the current last node of my linked list, so that I can add the new node after it. So to get access to this, so this will become easier when we have the tail pointer. So in some cases, just how we are given head pointer, we are also given tail pointer. Tail points to the last node. But in this case, let's take it easy. Let's just have the head pointer. So if I want to get to the last node, I can just traverse, right? And we already know how to do that. I'll create a temp pointer and I'll keep moving the temp pointer until my temp pointer next is pointing to null. All right. So until my temp pointer next is not equal to null, I'll keep moving it forward. So when will it become null? When it is at my last node. When it is at my last node, then my work is easy. I'll just change this link. I'll make the next pointer of temp, which is my last node, point to the new node, and the new node will point to null. Alright, and this is how I'll be able to insert at the end. And what will be the time complexity of this? The time complexity here would be O of n. Why? Because I'll need to traverse the entire linked list to get to the end node. If I'm already given the tail pointer, however, if I'm given the last node of my linked list, then it's a O of 1 operation. But if we are only given the head pointer, which in most cases will be only given the head pointer, in that case we would be required to traverse to the last node. So making it a O of n operation. Let's write the code for it. Void insert at end, and here again we'll be passing the head of my linked list by reference, and we'll passing the value of the new node that we want. So first of all, let's create our new node. So we created our new node, and now we need to traverse to the last node. You need to find the last node of my linked list. So for that, let's create a temp pointer starting from head, and while the next of temp is not equal to null, I'll keep moving my temp pointer one step forward. So at the end of my while loop, at this point, now temp is pointing to, at this point temp will be pointing to last node. Alright, so at the end, for the next of the last node, I'll add the new node. Alright, and I don't need to do anything else because the next of new node will already be pointing to null, right? Because that's what we have added in our constructor over here. We added a new node at the end after my current last node. Okay. Now here, if I'm given an empty linked list, alright. If I'm given an empty linked list, meaning my head is null, at that point when the temp will also point to null, right? And then when I try to access next of temp, it will throw an error, right? So before this, let's check, okay, let's add a check for the edge case. If head is equal to null, meaning the linked list is empty. So we can just call the above function, which is insert at head. Okay. So if our linked list is empty, we'll let this function insert at head handle that. Alright. Because if the linked list is empty, we won't be able to find the last node, which is what we need in this logic. We need to find the last node, but there is no last node if the linked list is empty. So, okay, common sense. Let's try this. Insert at end, and let's insert 4 and call the traverse function again here. Running this. And you see, this was my linked list after inserting 3 in the start, and this is my linked list after inserting 4 at the end. Alright. And finally, now let's see what I'll do to insert a node in the middle of my linked list. So we saw start and end, but also what if I need to add an element at some position that is given to me in the middle of my linked list. So for example, if this is my linked list, all right, and I'm being told to add a node at position 3, all right, so this is my position 3, so this is where I need to add my new node at position 3. Now to add my node here, let me draw it in the middle, okay, so easier to imagine. This is position 1, 2, and I want to make this as 3, alright. So for that, let's also draw the head pointer. For that, what I'll need to do is I'll need to change this link, right? So I'll need to change this link to point to this new node, and the new node should be pointing to this node after the position in which I'm inserting. Alright, so basically first of all I need access to this node, alright, so that I can change the next of this node, and this will be present at position -1. Okay, so if I want to add an element at some position k that is given to me, okay, let's call it k. If I need to add an element at position k, so first of all I need to access the node that is at position k -1, so that I can change its next pointer to point to the new node. Alright, and before I change that, I also need access to this node, which will be the node, if this is the temp node, or let's call it the previous node. So this is the previous next node. So before I change this link, if I change this link, I won't have access to the rest of my linked list, right? Because this is the only link that gets me to the previous, to this particular node. So before changing this node, what we'll actually do first is, we'll say the new node next, put it as previous next. Let's understand again, what am I calling previous? First of all, understand that previous node is the node that is at position k -1, alright. after which I need to add my new node. Now, previous of next will be the node that will come after my new node. So new node next of new node should point to this particular node. So once I have added that link, then I can change this link and make it point to the new node. So I'll first do this. I'll say next of new node, make it point to the previous next, and then I'll say previous next, make it point to the new node, and that's how I'll be able to insert an element in the middle of my linked list at some position k. What will be the time complexity? The time complexity here in worst case would be O of n. Alright, if position is the position at which I want to insert is the last position, then I would be required to traverse the entire linked list. That will make the time complexity O of n, or in average case it will be O of k. Let's see the implementation now. Void insert at middle. Here, first of all, let's take the head, we'll take the value of the new node, and also we'll take the position at which we want to insert the new node. Okay. First of all, we need to find the node that is at position k minus 1. Alright. And to find that node, let's create a temp pointer. Let's call it previous. Let's call this previous pointer because I want this to point to the node that will be coming before the new node. And let's also create a count variable, int count is equal to 1. Now, while count is less than position minus 1, I'll move the previous pointer to point to next, and I'll do count plus plus. So now my previous pointer is pointing to the node before, to the node that should come before new node. Okay, and let's also create the new node first of all. Node star new node is equal to new node with the given value. And now here I'll say new node next of my new node should point to next of previous, and now previous next should point to my new node. Okay, I hope this is clear that first of all I'm changing the link where my where the new node should point to the node that should come after it, and then I'm making the change for the previous node. And this code right here will help us insert an element in the middle, but in this what approach we are going for? We are first of all finding the element that will come before that position, okay, before my new node. Now what if I pass the position as 1? If I pass the position as 1, that means I want to insert an element at the first position, that means at head. Alright, and for that this logic will not work because here we are trying to find the element that is before that position, and there is no element before position 1. Alright, so let's add the check for that edge case as well. If position is equal to 1, if you're trying to add an element or node at the first position, then I can just call my insert at head function. I'll say insert at head and the value, and I'll say return. Alright, so in that case I don't have to go through the entire flow. Here as well we forgot to add the return statement. So here in insert at end, if the head is null, if our linked list is empty, after calling this function we'll say return, alright, so that the rest of the code does not get executed, or just add an else case, okay, whatever works, just add a return statement or else for this if statement. Okay, so let's try to call this function now. Insert at middle, let's say head 5, and I want to insert at position 3. And we'll call the traverse function again. So this was my linked list, and I inserted an element, a node at position 3 with value 5. Okay, I can also check for other position if I want to insert at position 2. So I'll be able to insert here. If I want to insert at position 1, then that will call just the insert at head and insert it at the beginning. All right. So this is how insertion in linked list works. Let's move forward to the next operation, which is deletion. And again, here we'll be seeing deletion at start, at end, and in the middle. Okay. So how do we delete an element from the start? If you are given a linked list, okay, and I'm given the head pointer. So this is should be pretty easy, right? We just have to delete the node that is present at head pointer. But also we'll have to shift the head pointer to the next node, right? If I just delete this head node, how will I know where my linked list is starting? Where will the head pointer go, right? So before deleting it, I'll first create a temp pointer, okay, which will be pointing to the node that needs to be deleted, and then I'll move the head pointer to its next node, all right, to the second node, and then I can say that you can free temp. Okay, we'll be using a function free that will free up the space that is occupied by this temp pointer node. Again, the time complexity here would be O of 1, right? We don't need to traverse the linked list here. Void delete at start, we'll be passing the head. So first of all, let's say node star temp is equal to head. I'll move it to the next node, the second node, which will become my new head, and then I can say free temp. Also, if my linked list is already empty, then there is no node, the first node, the second node, so I can just say if head is equal to null, means my linked list is empty, I can return. I don't have to do anything if my linked list is already empty. Okay, delete at start, or let's keep this uniform, let's call this delete at head. Alright, and I'll pass the head here and call my traverse function. So 3 got deleted here from the start of my linked list. Okay, deleting a node from the end. Again, here to delete the element from the end, the last node basically, I'll need access to the second last node, this node. Okay, this is my second last node. So using a temp pointer, I'll keep traversing my linked list until I find the second last node. How will I find the second last node? When my temp pointer's next becomes null. That means I've reached to the second last node. Okay, when my temp next, so if this is temp, the next and next, if that becomes null, then that means I have reached the second last node. When I have reached the second last node, I can make the last node, second last node, I can create a new pointer, temp or just last node. that will be pointing to my last node that needs to be deleted. And then I can change this link. I'll say the next of second last node should be pointing to null, and in the end I can free my last node. Alright, and the time complexity here would be O of n, because I'll need to traverse my entire linked list to reach to the end of my linked list. So let's write this function void delete at end, passing the head here. And what we'll do is, first of all, find the second last node. So to find the second last node, let's create a pointer temp, or let's call it second last node. Okay, so we know what we are going for. So I'm creating this pointer that is starting from head, and I'll say while second last node next is not equal to null. Till then, that time, move second last node one step forward. So this loop, when this loop ends, the second last node pointer will be pointing to my second last node. And what will be my last node? Node star last node. This will be equal to second last node nodes next. So next of second last node would be my last node. And then I can just say make the next of second last node point to null, and in the end free my last node. And for edge case, I can add an if statement here. If my head is equal to null, in that case my linked list is empty, so I'll just say return. And if my head of next is equal to null, that means I only have one element in my linked list. In that case also this logic will not work, because here we're trying to find the second last node. If there is only one node in my linked list, then there's no second last node, there's just a last node. Alright, so in that case I can just take help of delete at head function. Okay, if I am trying to delete one node that is present in my linked list, the last one node, then I can just call delete at head here. It will do the work for me, and I'll call return. Alright, so this will handle my edge cases if there is no node or only single node in my linked list. So let's call this function delete at end head traverse head. So here my last node was 4, and after deleting, this is the linked list that we have. Alright. Next part is deleting a node from the middle. So again here, when we are trying to delete from the middle, we'll be given some position k from which we need to delete. Alright. So for example, we are given k is equal to 3. So that means this is the node that I need to delete. So to delete this node, I first need access to the node that is before it. Right? I need access to the node that is before it. So I'll use a pointer, previous let's call it, to make it point to the node that will be at position k minus 1. So I'll reach the position k minus 1 just like I reached while inserting an element. I'll reach the position k minus 1 and get the previous node. Now the previous node's next is the node that I want to delete. Okay, so let's call this current node that I want to delete. And then I'll point where should the next of previous point? I'll have to change this link, right? So I'll make this point to this node. How? I'll say the next of previous should be pointing to my next of current, which is this. Okay, if this is current, then this is next of current. So this is how I'll be able to connect previous with the next of current, and then once I've done that, then I can delete this current node. Okay, and the time complexity here would be O of n in worst case, alright, in case I have to, if n is equal to k, I have to traverse the entire list. So void delete at middle, where we'll be given the head of my linked list and the position at which I want to delete element. Okay, so first of all, let's create a pointer for traversing. Let's call it previous and make it point to head, and also create another variable count so that I can count till k minus 1 position if the position given to me here is k. Okay, so while count is less than position minus 1, till then keep moving previous to next node, and I'll do count plus plus. So now previous is pointing to the node at position k minus 1. Okay, previous is pointing to node at position minus 1. Okay, if position is the value that is given to us. So the current node, the node that needs to be deleted, let's call it current node will be next of previous. This is the node to be deleted, and I'll say before deleting it, I'll say the next of previous should be pointing to the next of current. Okay, so the node that needs to be deleted, I'll connect the previous node of it and the next node of it, and then I will free my current node. Alright, again here to take care of the edge cases, we can just see, we can check if position is equal to 1. Then this will not work because we're trying to find the node that is at position minus at the position before the position that needs to be deleted, right? So that won't work when we are trying to delete the node at position 1. So in that case, I'll just call the function delete at head. Delete at head. So calling this function delete at middle, did we add a return statement? We'll also add a return statement here, so the rest of the code does not get executed in the function. So we'll say head at position 2 and then traverse head. So this was our linked list, and the element at position 2 was 5. So 5 got deleted from my linked list. Okay, if I try to delete the element at position 3, in that case 2 will get deleted, and if I try to delete at position 1, in that case 1 got deleted. Alright, so this was insertion and deletion. One last thing is updation of a node. If I want to update a node at a particular kth position, so again you should be able to do this pretty easily. If I have a linked list and I have some position k and I want to update the value at that position k, okay, for example k is equal to 3 and I want to update the value at this position, so I can just use a temp pointer that will be starting at my head, and I'll keep moving it till I reach k position, and at that position I can update the value. So this should be easy, right? Let's just implement this quickly. Update node value. So I'm given the head and I'm given the updated value. Let's call it updated value, and I'm also given the position at which I want to update. Okay, so let's call it k. So I'm given three things: the head of my linked list, the k position at which I want to update, and the updated value. So first of all, we'll create a pointer temp, make it point to head, and let's also create a counter which is equal to 1. Now while count is less than k, we'll keep moving our temp pointer by one step, and we'll keep doing count plus plus. So now our, after this loop ends, that will end when our count becomes equal to k. At that point, our temp will be pointing to the node at kth position, and now I can just update its value. I can say temp value, make it change to the updated value. All right, so right now what is the linked list that we have in the end? This is the linked list that we have. If I want to update node value in this linked list at position 1 with value 8, let's see if our function works. So now you can see here at the position 1, I updated the value from 5 to 8. Okay, you can also update it at position 2, from 2 to 8. Alright, so this is how we insert elements, delete elements, update elements in my linked list. And also, what is the time complexity for updation? It will be O of k, and in the worst case this will be O of n, right, in the case that k is equal to n. Now let's test whatever we've learned so far in linked list and try to solve some questions, starting with very easy level questions, and then we'll, in the coming videos, we'll move forward to medium level questions, and we'll cover some hard level questions as well. So the first question is, given the head of a linked list, we have to delete every alternate element from the list starting from the second element. Alright, so if this is our input, the output looks like this, where we're deleting the every alternate element starting from the second element. Alright, so let's try to see how we can implement this in code. Let's start with 4 elements. If we're given 4 elements, okay, and we need to delete every alternate element starting from second element, meaning we need to delete this one and this one. Okay, and obviously the head of the linked list will be given to us. So we need to delete the element that is after the head, right? So first of all, let's take a temporary pointer, okay, through which we'll be traversing our linked list. And if we start our temporary pointer from head, we need to delete the node that is after my temporary pointer. So where would the next of temporary go? If we delete this element, where would this link go? This will go to the element after the node that we are deleting. Alright, so what we'll do is we'll call this element as delete node. Okay, this is the node that we need to delete. Okay, let's call it delete node. So delete node will be the next of the temp node, and the next of temp, meaning this link, will remove, and we'll make temp next point to temp next next. That means this node right here. So now temp next is pointing to the node that is after the deleted node. Alright, and now since I have changed this link, I can conveniently delete this. Now I have to repeat the same thing till I have deleted all of the alternate nodes. So I'll just move the temp to temp of next. So I'll move my temp pointer to its next, which will be here. And I'll go through the same process again. I'll say, okay, this is the node that needs to be deleted. This we've already deleted. And we'll change this link. We'll change this link and make it point to null. So temp of next will point to temp of next, which will be null here, and then we'll delete the delete node and we'll move the temp to temp of next. So we'll keep doing this till the temp reaches null. Now the temp will reach null in case of even elements. What if we have odd elements here? Instead of null, we have another element here. So we have odd elements, odd number of nodes, and this is pointing to null. In this case, when I do temp is equal to temp of next, basically my temp pointer will come here, right? So again here there is no node after this that needs to be deleted. So in this case my stopping condition would be when temp of next becomes null. Okay, so when I have even number of nodes, my stopping condition would be when temp becomes null, and when I have odd number of nodes, then my stopping condition would be when temp of next becomes null. Alright, so we don't actually need to count if we have odd or even nodes. We just keep the stopping condition if any of this condition occurs first. If temp becomes null, we reach the null pointer while traversing through temp, or the temp of next of temp becomes null. In both of the cases, we'll stop traversing. Alright, and we'll return whatever the list is currently. So let's see this in code now. So we'll use the class node that we already created and the basic functions that we have seen to create a linked list. Let's first create node star head is equal to null, and then we can use insert at end function to just insert values into my linked list. So let me just copy paste this and change the values here. Perfect. Alright, so I have a linked list. You can call the traverse function to see what our linked list looks like, and we'll take this linked list as an input to to get the output for deleting every alternate node. Okay, so let's write the function for that, delete alternate node, where we'll have the head of our linked list. So what do we do first? Let's first try to see, let's first try to create our temp pointer, okay? That would be starting at head. And we basically need to keep moving this temp pointer forward till the entire linked list is covered and we have only the alternate elements left. So in the while condition, we'll say until temp is not equal to null, and so we're putting and condition here. So if any of these condition becomes true, we will just stop there. If temp becomes null or next of temp becomes null, in both these conditions we'll stop traversing. And next we find what is the node to be deleted. The delete node will be next of temp. Okay, this is the node that we need to delete. And before deleting it, let's first alter the links. So now temp of next should be pointing to next of temp should be pointing to next of temp. Okay, because we want to leave out the node in the middle, and we'll move the temp pointer to its next node. In the end, we can free up the delete node. All right, and here we can already see that the while condition will be taken, the edge case will be taken care of. If the linked list has is single, then this will never be called, right? And if the linked list has only one element, only one node, even then this loop will not run and nothing will happen, right? So we're good. So let's try this out. Delete alternate node, where we'll pass the head node and then traverse and see what our linked list looks like. So this was our linked list, the one that we created, gave it as input, and this is our output, right? Where 2 and 4 are the alternate elements that have been removed. What if we have odd number of elements? Let's see if our code still works for that. So I just added another node at the end, which is 5. So again here we can see 2 and 4 removed as the alternate elements. So our code works, and what will be the time complexity? The time complexity of this operation would be O of n, right? Because we're traversing our entire linked list. Moving on to the next question, which is finding the middle element of a given linked list. So given a linked list, we have to find what is the element that is right at the middle. Okay, so one way to do this is to find the length of my linked list. So for example, if I have this linked list, I can traverse the entire linked list like I do for printing, and I can count the length of the linked list. So here the length will come out to be 5. So if there are 5 elements in my linked list, so I know the middle element would be present at 5 by 2 plus 1, I can say. So that means that the middle element would be present at 3rd position, which is this. Firstly, we'll need to traverse the entire linked list to find the length of the linked list, which is easy. We know how to traverse the linked list. We just need to keep a pointer and keep increasing it to find the length. And then we need to traverse the linked list again till the middle element to return the value of the middle element. In this solution, we'll be traversing our linked list twice. Okay, first we'll be traversing the entire linked list, and then we'll be traversing half of the linked list. This is of course a valid solution that we've just discussed, but there's another slightly more optimized solution to this question as well, and for that we follow the approach of slow and fast pointer. Slow and fast pointer. So try to understand, for example, we have a racetrack over here, okay, and there's one person called slow, another person called fast, okay. Now the slow person moves with the speed of x, let's say, and the fast person moves with the speed of 2x. So basically fast person is moving with the speed double of the slow person. So in the same time, if fast is covering this entire distance, d, let's call it, the slow person will cover only half of the distance. Does that make sense? Because fast is moving with the speed of, is moving at double the speed, then that means in the same time, fast will be able to cover double the distance because fast is moving at double the speed. Okay, so with that approach, we can use that to find the middle element, because when we can say that the fast, in the time that fast will cover the entire distance, that means in the time that the fast will cover the entire linked list, the slow will cover only half of the linked list. And so I can say when fast reaches at the end, slow will be at the middle. When fast reaches at the end, slow will be in the middle. So now how to imagine this in a linked list? Of course, there are no persons running in a linked list and there's no speed, but we'll be talking about pointers here. So try to imagine we have a list here, okay, and this is our head. What we do is we take 2 pointers. One is slow and one is fast. Now I am saying fast is moving at double the speed. That means if slow is moving by 1 node, then fast will move by 2 nodes. If slow pointer is moving by 1 node, fast will move ahead by 2 nodes. So in the first chance, slow reaches here and fast reaches here. In the next chance, slow will reach here and fast will reach here. So fast is moving by 2 steps. Now here fast has reached the end of my linked list, and so slow will be at the middle of my linked list. So if you see this is for even elements. So in even elements, when my fast pointer reaches null, then that means my slow pointer would be at the middle element. And if we have odd number of elements here, okay, if we have another element here and this is pointing to null, so when fast reaches here on my last node, again my slow would be at the middle element. So I can say the fast element, when it reaches null or it reaches the last node, at that point my slow pointer would be at the middle node. Okay, so common sense, like really the intuition behind this solution is just that if something or someone is moving at double the speed, then at the same time they'll be able to cover double the distance. Or another way to say it, if something or someone is covering has a speed of half, has half of the speed, then they'll be covering half of the distance in the same time. So slow is covering half of the distance in the same time that fast is covering, okay, the full distance. So slow will be at the middle element when fast reaches the end of my linked list. Okay, so let's see this in code now. Void find middle node, where I'm passing the head of my linked list. Okay, so we already have a linked list created here. Just need to write the function for finding the middle node. So we'll create two pointers, slow and fast, both will be at head in the beginning. And we'll say while fast is not equal to null and fast next is not equal to null. Till that time we'll keep moving forward. This basically means that till the fast pointer doesn't reach to the end of my linked list. Okay, so if there are even a number of elements, then the loop will be terminated by this condition. If there are odd number of elements, then the loop will be terminated by this condition. So till this happens, I'll keep moving the slow and fast pointers in the way that slow will be moving by one node and fast will be moving by two nodes. Okay, so slow is equal to next of slow and fast is equal to next of fast. All right, and when the fast pointer reaches the last element or null, at that time slow will be at the middle element. Slow is now at the middle node, so I can just return, let's change this to int, and I can return the middle node value. So slow value I can return from here. Okay, and here let's try to print find middle node in my linked list. Running this, so this is returning 3 to us in my linked list. Okay, and if I add another element here, then again here also 3 would be my middle node. So in today's lecture, we were able to see what is linked list. We saw the basic operations, insertion, deletion, traversal, updation, and we solved a couple of easy level problems. In the next video, we'll be looking at some medium level problems on linked list. And that's all for this video. Thank you so much for watching. Do practice all of the questions that we discussed in this module. And if you have any doubts, drop them in the comments so that we can get to them.